for example, people who are applying graph theories and various kind of things. And to understand which sequence will form into this structure, like alpha helix or beta sheet, was very, very hard to do it. So now, again, using the same group of people, the AlphaZero, DeepMind people, they actually built a system that is now performing exceptionally well. And the people say that this tool is such an influential in biology. For example, to do from the primary sequence to tertiary sequence, sometimes you have to spend a year to come to that point. So now that could be done in few days, for example, or few hours. And previously, a sequencing of a complex structure, having, let's say, 1,000 amino acids might take, $100,000 or more to come up from a linear sequence, which could be done very cheaply to produce a tertiary structure. And now that all could be done using deep neural nets. So basically what it's doing is you give the sequence and produces the structure, how the protein looks like. So from this, you can predict its function. What it does, if there is a slight mistake in the sequence, maybe the fold would be entirely different and therefore the protein doesn't work anymore. On my own work, what we did is we looked, for example, diffusion MRI. From that, we can actually predict underlying health of a human brain. For example, we can see which part of the brain is actually functioning correctly using the diffusion MRI, and then associated functional MRI. We were able to connect association between the structure of the brain to its functioning. So this is a big challenge which was impossible to do before. Now with all these deep neural nets, we can do that. And similarly, for those who are in computational fluid dynamics, they find that when you have a blood vessels like this, and if the blood is pumped from one end to the other, you wanted to know what kind of stress that these blood vessels have. And for example, in mechanical engineering or chemical engineering, they try to understand how the fluids flow. So they use these computational fluid dynamics, and sometimes this will take days and probably even weeks to compute the stress levels of these things. So we decided to apply deep neural nets, and we were able to do in less than a minute an accuracy very close to 95% of computational fluid dynamics. And one of the things we have to remember is that computational fluid dynamics itself is a mathematical model of what the fluids move. So in reality, they would not be exactly the same what a patient might be experiencing, but they would be close enough. So our model probably just as close to the reality there as is the computational fluid one, but this computation using computational fluid dynamics might take several days, whereas we can do that in 2 or 3 minutes. So what it means is that some of these techniques can be applied in real time when the surgeon is actually doing a surgical procedure on the patient. So first thing they do is they send a small probe using one of these optical coherence by the GPT kind of tool. So this is a problematic. Or have they taken some assistance from GPT and then based on that they rewrote their own? So it is causing lots of stress for academics, because for them, without studying any textbooks, they're writing high quality stuff using GPT, for example. Can also produce wrong answers. GPT can be really bad, especially if you tried any, anything like DAXA kind of algorithms, like dynamic programming kind of problems you're trying to do. These are terrible. They can't work. They can't work well. So the point I wanted to say is if GPT does wrong, we know that even we do many times wrong. The experts do mistakes, but current AI systems make more mistakes. I mean, because they are very early systems. So the way I see GPT is what the early days of IBM PC was. Now the PCs are so powerful, and I think all these models will become incredibly powerful in the next 10 years. And that would be mind-boggling. And they can handle and translate many languages, like hundreds of languages. And these huge language models are, as I said earlier, like 175 billion parameters, trained on, half a billion or half a trillion tokens. Uses both supervised and reinforcement learning. For example, GPT 3.5 and GPT-4 are large language learning models with human input, because they were, the reinforcement side was actually with human input, and they're applying reinforcement to make them more robust systems. They mimic human conversations. It can code and debug computer programs, compose music, write essays, answer test questions, pass many exams, and some of the reported results were apparently the GPT-4, I think, scored 88th percentile on the law school admission test and did even better on the bar exam. And it is not surprising, because you say the entrance he didn't do that well, but in the bar exam, I mean, those people who get into the law, after getting into the system, it didn't do that well, 88th percentile. That means 4% of the population of the students done better than GPT-4. But in the exam, in the final exam, it is done better than most students. Those who got into the system, it is doing better than 90% of them. And it's unsurprising. Part of the reason is the law school admission would be more general tests, which would be much more difficult to train a system. Whereas bar exam is very focused area, specialized area, and all you need to rely on the law documents and nothing more. And whereas in the case of admission test, it is more general. So the kind of knowledge needed for training is much more than training as a lawyer. So the point I want to make is the more specialized the area is a lot easier to train these models, which is kind of strange, because we tend to pay more money for a specialist than a generalist. You pay a small amount for a GP, but you pay a lot of money for a specialist. But in reality, the GP knows a lot more than a specialist, as you can see in this argument. GRE is, this is for the, if you were going to any of the American universities, you have to do that. Again, quantitative 80th percentile, verbal 90th percentile, writing at that time is 54th percentile. So that's because you can see text writing is much more. Cost of medical examination. So you can see that, how powerful this. So there is a rumor that GPT-5 apparently does postgraduate level in many areas. That means it can do some challenging mathematical problems. If that is true, I think that is very close to artificial general intelligence in my view. So that means if it can perform as well as any postgraduate in mathematics or computer science, then that is exceptional in their performance, especially in the mathematics. In computer science, again, at the algorithmic level, is very difficult like mathematics, but some of the coding side is not so difficult for these things because it's more like language kind of models. So these foundation models are basically, built like software engineering, built on many libraries that we have. Like for example, if you're building any computer system, you generally use lots of libraries. If you're a mathematical programmer, you will be using math tables, Fourier transforms, depending on what area you do. You basically use all those tools to write your application. Or if you're a accounting person, you will be using some relational database and build systems on top of that. Applying local taxation rules, how much you have to charge on what various kinds of activities and so on, how much tax you do. So basically you put those rules, and then that's how you build these systems. So everything basically use libraries. Or sometimes already the system's built, all you do is you tune parameters. So if you choose particular parameters, it's actually programming. Choosing parameters is nothing but programming. So these are basically, in the case of machine learning, these are basically transfer learning. Basically what people have built many AI models, and you use them for your application. A foundation model, generally a single huge model trained on large amount of general data, then adapt the model to the new problem at hand. Whereas we used to train the model, start from the scratch and build a problem. It's too expensive, very difficult to learn, and generally do not perform as well. But if you use these foundation models, they've been tuned well and they do exceptionally well. For example, GPT-3 for doing some language modeling, you can use that using their API. And Bloom is another example. BERT is similar. And similarly for the images, DLE2 for image handling. Currently these models are not practical for most institutions and organized. They need huge computing infrastructure, except maybe through large CPU clouds. So, for example, some of these foundation models you can get, GPT from OpenAI, BERT from Google, Lambda from Google, PALM from Google, Bloom, Hugging Face, Llama from Meta, Claude, Anthropic. So you can see these are all foundation models that one could use. And also remember I told you that these are very expensive to build. So for example, to train Llama, which is the Facebook Meta one, their system, they use the 7 billion parameter, which is the Lambda 2, and there's another version, I think 70 billion one. You can see the number of GPU hours is 1.7 million, and if you rent it, it's going to cost you to train that model about $1 million. Assuming $1 for GPU hour, for example. At that scale, you can get that. You can do that. So if you have a 100 billion model, then you have 1 million GPU hours. For 70 billion, it's something like that. So if you're going to rent, 100 billion model Llama, if you're going to train yourself, excluding all the effort that's needed for the preparation of the data and so on, even if you have a clean data, you're thinking of $1.5 million every time you run this system from scratch. And if you're going to build a system so that you don't have to pay rent, then you're thinking of $10 million. So if you're going to be a researcher in this area and you need huge amounts of cash, either to have your own GPU cluster or be able to pay rent. And remember, this is just the machine cost. Then you need maintenance, and you need rooms, air conditioning, and then you need to spend for the programmers to maintain the system and so on. Some challenges in the AI is that data acquired may not be complete or even representative. So today, AI models can still misbehave badly because there is some bad data on the internet, and sometimes whatever the precautions these guys, you know, OpenAI and Microsoft or Google, trying to make sure that bad data is not fed into these model training, it is impossible to eliminate that. In fact, my second statement states that unfortunately, no effective computational procedure will exist. When I say effective, that means 100% proof. Will never exist. This is basically one of these undesirability results, because you can always write a code that looks harmful when it is not, and similarly you can produce a data that looks innocuous but it's dangerous. So let's say, for example, you do not want these machines to learn how to make a weapon, for example. You might put a lot of keywords to stop it, to eliminate that data, but people might find other names to these complex things. Maybe a coded version of the text is put in there, and then whoever knows that code can see this data and then really understand how to make those weapons, for example. So it is impossible to have a procedure that stops bad data. And as I said, there's also a notion of completeness. That means I have all the information related to this particular problem with me. That kind of thing we never know. So we have, and the other issue is that we have acquired so much knowledge, through our research. Last I don't know, let's say 5,000 years of human civilization, that we know how to build pyramids, about 8,000 years or 7,000 years old, to various kind of novels people have been writing for many years, and we have a lot of basic knowledge of biology, cultivation and everything from various parts of the world. We collect all this knowledge, and some of them is actually documented, but we don't know how to use this knowledge into AI models seamlessly. For example, can AI machines learn whole quantum mechanics, for example? Can it understand relativity completely? So, for example, if I give a relativity problem, can it solve it? Right now, it can't. So for example, GPT language, I think the GPT-4, I believe, or GPT 4.5, they introduced, if you pay money, you can also do some image understanding and image generations, I believe. So my question is, can we ever build a model like GPT to do serious mathematics, produce new mathematical theorems, new physics discoveries, explain dark matter, dark energy? There are some new results appearing, which shows that maybe it is feasible in the future. We can't tell, but there are some. I understand some of these AI models, large language models, was able to discover new answers. Some of the well-known, open mathematics problems in terms of solutions they have given, but I don't believe they have so far come up with some new theorem that was never known before. So can we teach our AI machines to produce next prime number to a given number algorithm without algorithmically? That means, can I feed the data continuously? This is the prime number, this is the prime number. Does it understand what a prime number means in a coding sense? Can it write a recursive program to show what constitutes a prime number? For example, can it say a prime number is a number that is not divisible by any number, for example, except, which is one is not considered a prime number. So that kind of model, can it infer from simply looking at these numbers? And I believe it cannot. Okay, so how do we integrate domain knowledge? For example, best examples are CNNs. CNNs basically integrated domain knowledge. So surprisingly, in the case of computer vision, we have an idea that some structures need to be looked at. Suppose, for example, let's say if I'm building an AI machine that recognizes birds from the rest of the images, then I can train this model looking for various parts of the bird. For example, a beak, and maybe eye of a bird, and then structure of the feathers and so on. So this is basically done, understanding how images look like. The CNNs are basically done that. Basically what the CNN is doing is that discovering feature extraction for these for recognizing images. Similarly, the text analysis like transformers, they also use effectively a form of convolutional neural nets, but done in kind of parallel way. And then if you try to do just a decision, then maybe the final layers tend to be fully connected deep neural nets. And of course today, the most important things are attention and transformer networks, and ResNet. And in the last, I think in December last year, that is a month ago, someone proposed a new kind of learning system, which is based on state space models. Those who were trained as electrical engineers, we know, for example, how feedback networks we try to do it. For example, you write a state space equation. For example, x dot, the derivative of some variable x equals some matrix times the x itself plus some matrix times the input, and then you do the output model in terms of this hidden variable x. So that is the state space model. Now they have came up with a model called Mamba, which basically saying that you can reduce the complexity of these attention-based networks by using simply this state space S6. They were showing phenomenal improvement over these transformer networks. This is which are basic components for large language models. Except, as I said earlier, they could not build as big a model as, for example, GPT-4 or Bard from Google to compare the results, because you need a lot of money to do that. But they did build a model which seems to be challenging on the similar kind of network. So, for example, I think Mamba was trained up to, if I remember correctly, up to 7 billion parameters, and then you compare a GPT-3 with 7 billion parameters, and this is outperforming them. One of the things they showed is this Mamba can remember up to tokens of 1 million tokens. For example, GPT-4, I think, can only remember, its sequence memory goes up to 4,000 tokens. Or something like that, or 64,000. Whereas this one goes up to 1 million. So it's already showing that these kind of state space models, which is usually bread and butter of control system people, are now embedded into deep neural nets, and they are making some breakthroughs. One of the nicest things is in the state space model, the mathematics is much well understood than these transformer networks, for example. So foundation models are basically built using the deep neural nets of these kinds, CNNs and DNNs and attentions, and now probably Mamba as well. Apparently Mamba is a fast-moving, highly venomous snake. That's what the name they have given this particular S6. So the question I have is, how can I make AI model to explain the reasons for its decisions? So for example, let's say an AI system suggested something, some medicine to be administered, and let's say when medicine administered, it adversely affected the patient, and then they take those AI, whoever applied AI, they take them to the court, and then the person needs to explain why that medication is prescribed. Now the question is, this AI model has to explain why that particular suggestion it made, and that needs to be explained. And I believe in Europe, they were saying if you're going to use AI in any of your applications, you should be able to explain the reasons behind those decisions. There is no general deep neural net foundation model that allows us to integrate domain knowledge or scientific knowledge seamlessly while training the model. So for example, let's say I'm trying to build, let's say, argument's sake, a GPT version for the whole of physics, that understands quantum mechanics, that understands general relativity. You remember anything related to physics. So I should be able to pose any problem to this particular physics problem, and it should do it. Now the interesting thing is that you can feed all the text you want to, all physics books ever written, you can feed it, but it won't be able to solve, let's say, a particular problem given to it on general relativity or on quantum mechanics. So the reason you need to do is that some of the algorithmic knowledge need to be fed into the systems, and how do we do that? We don't have any clue yet. One possibility is to include the domain knowledge through the loss function. One of the things you should understand is that machine learning basically has three aspects. I'm ignoring the data, I'm ignoring the computational power, I'm assuming that are given. The first thing is you need to choose the model. What kind of model? Do I use a CNN, or do I use attention, or something like S6? This is the first decision you have to make. And the second decision you have to make is how big these models to be. And the next one you wanted to do is, what is my loss function? That's an important part. The loss function basically tells you what you are tuning this system to be. And of course, once you have decided loss function, then you need to build a model, which is the back propagation and the optimization function. So a lot of work done in optimization, stochastic gradient methods, various kind of optimizations were done to learn these models fairly robustly. But the important thing is the loss function. So my point of view, what is programming involved in a machine learning is basically choosing the kind of architecture and then choosing the right kind of loss function. And again, these loss functions can make a big difference how these models behave. So some of the things that I want to cover is that in machine learning, we use the distance between two data points to see how similar they are to each other, or an angle between two data vectors. So this is how we use loss functions. So for example, let's say you get one answer by using this model, and you know the real answer. You want to find the difference between them. And this difference between them is basically used using, using mean squared error. You subtract each corresponding element, and then you basically treat it like a n-dimensional space. You're finding the distance between these two data points. So if the distance between them is 0, means that you have a perfect answer. If the distance is very far away, that means it's a wrong answer. Unfortunately, our data has many features, and these features, we don't know how they're related to each other. They may not be orthogonal to each other. They're not like Euclidean geometry. Like, in Euclidean geometry, you have all these coordinates. They are perpendicular to each other. So you can simply apply Pythagoras' theorem to find the distance between 2 points, or finding an angle between two vectors, for example, unit vectors, using dot product, or in this case, you subtract corresponding coordinates and then square them, add them, get the square root, and you get the distance function. This is basically Pythagoras' theorem. And the interesting is we can't apply Pythagoras' theorem on the arbitrary basis vectors. So for example, let's say age. Let's take a particular data set that has age and gender. Is age and gender, are they perpendicular to each other? I don't know. Maybe, it is perpendicular at one point, maybe at one point it's not. For example, let's say if somebody is living longer than 100 years, the chance of that person being to be a female is higher. So that means it's not perpendicular anymore. There are some correlation taking place. And similarly, the weight versus gender. Maybe men will be heavier than, let's say, on average compared to female. Or the height. Generally height is much higher for a male than a female. So if you have height and gender, again, they're not necessarily perpendicular. So therefore, thinking of Pythagoras' theorem, or using the angle between two vectors, we can't use this Euclidean geometry. So this is where we, amazingly in physics, when you do general relativity, you basically needed to understand the metric tensor. So basically, the space-time is curved, and therefore you really need to use the appropriate metric tensor to find the distance between 2 points. So for example, if you have 2 points P1 and P2, they are not non-orthogonal, or they are manifold spaces. That means curved space like a sphere. Then you have to do this. You have to subtract P1, P2 like normally you do, take its transpose, and if the coordinate system is completely Euclidean, then this G matrix will be identity matrix. Otherwise, you need to discover this metric tensor to find the distance between these 2 points. This is for the distance. And similarly, if you want to do distance between two vectors, you do P1 transpose G times P2 if you want to find the angle between them, for example, dot product. So this is what I showed you. P1, P2 are two unit vectors in non-orthogonal spaces. If the angle between those two vectors is theta, then the way I have to do is cos theta is P1 transpose, and then you have to have this metric tensor and then P2. So this metric tensor need to be estimated. So in our data, for example, metric G is important in measuring distance in curved spaces, non-orthogonal space, manifolds, or general relativity. So we have no clue in what space our data resides. So you collected huge amount of text data. So maybe these words are not perpendicular. So for example, you take the space, queen and let's say royalty is one vector, and another vector is let's say gender. Of course, they are correlated. For example, king means man, queen means female. They're not orthogonal in that sense. They are correlations. So you need to really learn this metric space G, and this is what you will find in many new models. They are actually discovering this G matrix by using machine learning. Similarly, for example, if you look at covariance, if you have two vectors x and y, you wanted to know how well they're correlated. Normally, this is what you do: x minus ex, y minus ey. What happens if the elements of x are correlated? That means, some elements, they're somehow dependent of each other. This correlation is not a good measure. So what you really need to do is needed to introduce your G matrix in this, so that if there are any correlations within x and y vectors, they will be taken into account by using this metric tensor. So you can see covariance is a kind of cosine function. If you assume this x and y are unit vectors with mean value 0, you're doing x dot y, and these are unit vectors. X dot y is nothing but cosine theta. So you should remember covariance is a factorially cost function, and that's what you should remember. Okay, so maybe I skipped it. So here is a manifold, for example. So think of this is like a folded sheet, for example. So this is how it is residing in a higher dimensional space. And what I wanted to say is, let's say all the points in the top part of this surface belong to class 1, and these belong to class 2. So for example, if you try to find the distance between P1 to Pk minus 1, if I just use, let's say, standard Pythagoras theorem, then this distance will be much higher than this one. We think it is much closer. But in reality, P1 to Pk should come all the way around this loop. Pretend it's like a ribbon, and if you expand it, P1 and Pk were far apart compared to Pk P minus 1. So what my metric tensor G is trying to tell me is how to compute this distance. The G tells me the shape of this curvature, and it tells me how to measure the distance in such geometries, for example. Okay, so that's the basic why we need this kind of matrix. So quickly, and how the neural nets work is, like for example, DeepMind was bought by Google by paying, apparently I think, a small group of people from UK, and paid them $400 million. And now Google is one of the top AI groups. They can beat the best games in the world, both in biology and also in games, and they also produced the very fundamental, attention all you need, these transformer networks that became such an important contribution to all of those machines. They all use the same technology. So this is the group that actually produced those results, and this is the Google also bought people from Canada, Jeff Hinton and so on. These 3-person startup group as well, and similarly, millions of venture capital dollars, were put into various kind of companies. So you can see that the AI is a very hot field, and I think some of the recent wealth creation seems to be the AI technologies these companies have. And surprisingly, today's mobile phone has a lot of AI component in them. When you're dictating, it is using AI. When it's predicting your next word, it's using AI. It's recognizing your face using AI effectively. Deep learning has won numerous patent recognition competition. That's so with minimal feature engineering. You can see what's happening. This wasn't always the case since 1980s. The models hasn't changed, but the important thing is more hidden units, better optimization techniques like stochastic gradient with appropriate tuning for those models. For example, how to use your delta variations to do that, the learning rate, how you control the learning rate and so on, and the new nonlinear rectified linear units. So now there seems to be the better functions seem to be something like SILU, which is basically product of x multiplied by sigmoid function, and that seems to be the state of the art now, which is being used in Mamba, for example. There are faster computers and GPUs, and how to optimize these things, and also many language models people have built. So basically, what we have is you're given a data set with some independent variables and then dependent variables, and the question is we need to find the relationship between independent variables to dependent variables. That could be some function, and this function could be, if it is a linear function, it's just a linear function, and if it is some deep neural nets, it's some kind of nonlinear, it's a convolution net, or it could be one of your transformer network, for example. Now, important thing is that these functions have parameters, and you have to estimate these parameters. These parameters are estimated by simply finding the values that minimizes the difference between the predicted value y hat to the actual y on your known data set xi and yi. So basically this is what we're trying to do. So the last function could be, as I said, like mean squared error, but you could even have more sophisticated error studies. You also want to discover some kind of a metric that would be ideal, but again, that metric in the last function is a lot more trickier to than we can anticipate. So for example, here is what we're trying to do. You've given your data, and this is the function that I'm going to estimate. The parameters that I have to estimate is theta. So the idea here is that choose the optimal theta such that this function, which the last function, which could be least mean squared error, which basically you apply the independent variable xi, and it predicts the output, and then you find the difference between the prediction to the actual, and then you want to minimize on every data that you are using in training. So this is how the machine learning works. So the way we're going to estimate is this using stochastic gradient method, which is basically saying that in the next iteration, I'm going to update my theta values using the old values, theta t, and then I do a derivative of this function, the last function that we used, applying that function. So basically you do a derivative of this last function using this f, and then this is the learning rate at which you want to adjust these values, and then you keep on iterating over and over until you think that theta is not changing too much, or you put some limitations of how much computational effort you want to put in tuning these values. Apparently, this is the most executed computer program on the earth now, because these machine learnings are keep on running this particular stochastic gradient code forever and ever. So this is the most executed code, just a curiosity. Okay, so the important thing to notice is that when we try to estimate this theta 1, theta 3. So remember, this is a dot product, but what we're doing is effectively assuming, let's say, this theta 1, theta 2, theta is a unit vector, and this is also a unit vector. We're doing a dot product. That means I'm actually looking at cosine similarity. What I wanted to do is discover these theta 1s that best match for this particular feature. So basically, for all the inputs, I'm trying to find the best theta 1 that I can use, and then basically something like this, which gives you values. What you're doing is you are also multiplying the sigma a by a itself. That is, a times sigma a is called psi loop, which is a Swedish linear unit. And of course, you can have not just one hidden unit, many hidden units. Basically, what I'm trying to do is, if you remember, basically I'm discovering various correlation vectors so that I can build many such correlation vectors and then generate these hidden variables to which I can use my sigmoid function to label these things. So that's basically what a typical neural net is doing. So the important point that I wanted to emphasize is that deep neural nets are basically doing a kind of similarity functions at each level, and these similarities done by these estimation of these values. So in the case of large language models, these number of arcs that you are computing, they are something like 170 billion or even a trillion of those things. So this is the kind of pipeline you given some input, you compute the hidden layer values, and then you pass through some sigmoid function, and then you do again another output linear, and then finally you do the sigmoid, and that is your decision variable.
Sir, sorry for interruption, sir.
Sorry?
Sorry for interruption, sir. Sir, due to insufficient time, can you just finish up in 5 minutes,
okay.
sir?
Okay, so I will try to finish.
Sorry, sir. Sorry.
Okay, so basically, this is what's happening in all these networks. Okay, so because we don't have much time, I'll skip quite a lot. A lot of you would know that. But the important thing I needed to do is these are basically kind of cosine functions. Okay, so I will go straight to transformer networks and then summarize my talk. Okay, so one of the things we're trying to do is, in the case of sequences, what we're trying to do is we basically okay. So in the case of recurrent neural nets or sequences, you give some input, you find some hidden layer, and then what you do is in the next layer, in the next computation, you're going to feed the hidden input. That means previous state is used in the computation of the following state. So if you expand that, this is basically an expansion. Initially, let's say null, we don't have any hidden value. First input comes and then you get H1. For the H2, what you're doing is you're taking this H1 and then feeding along with X2 and computing a new H2, and then of course based on H1 you predict Y1, based on H2 predict Y2. So basically this is how you're trying to do. So interesting thing is in the learning process we're trying to update our U matrix and W matrix based on our input sequences we do. And these can be used for language prediction. So you given sequence you can predict various outputs. So for example, sequence to sequence models, you're basically doing parallel outputs. And if you're going to translate something, you give some sequence and you finally hit pull and use that one to generate output exactly the same way for translation purposes or completion purposes. So one of the difficulties that I found is that the single state controlling the generation output, and that became very difficult. So this is where the attention networks came, and what you're basically trying to do is you're trying to provide whole context at every level, and the context is generated using this particular function. Basically what you do is you do the hidden exactly the same way we did, and the context is used using all the hidden outputs, and then we feed it into CI. And the CI is defined by alpha, ij, he, ij. These are the encoded states. The question is you needed to know how alpha ij is generated, and this is where the attention comes into purpose. And you can see that the score is again computed using this metric tensor kind of model WS. And that's what makes these models very effective. And then what we do is that, basically the CI is specialized at each level, and then you're feeding them. And this is what is taken by their transformer networks, and they have used in their encoding. Basically what you do is you feed this information using the self-attention. This is the interesting part of the transformer networks. Basically, as I said earlier, you take your input X1, and then somehow the model will build these kind of tensors, geometric tensors, and then to get the query, you get this W matrix is built. And then you get Q1 is like this, geometric tensor that I was talking about. And similarly, the key value in use again X1 on this one and do. So these matrices are actually built through back propagation. And once this is done, then you basically, for given X1, you try to get all this. So this is how the attentions are done. So Q1 is basically uses these vectors and other states, and gets this value, and then of course these are somehow normalized using some sigmoidal function and also the other things. And finally the input X1 is converted into a hidden state Z1 using all these structures, and you can see how this is coming from the other matrices. And similarly you compute Z2 and then you compute many such heads and do that. So what I wanted to quickly within a few minutes is that these deep neural nets, you can do the foundational networks, and if you wanted to include domain knowledge, you can include the domain knowledge in your loss function. So for example, let's say if it is some kind of a automated system to do self-driving, maybe in the loss function you should put that certain behaviors will be finalized if it's predicted. For example, let's say it directs you to go 300 miles per hour, for example. Then you can constrain that, saying that speed should never be exceeding, based on the space, the expected speed should be less than 60 kilometers or 30 meters or some kind of knowledge we can build into the loss function so that the deep neural nets doesn't behave badly. Or we can have, let's say, explanations. Again, you can have input and deep neural nets, and then you train for your particular problem. This is the foundation model, and then I can use deep neural net for explanation, for example, and then combine them. These dotted lines basically tells you propagation, back propagation doesn't go there. These are fixed ones. Only the learning modules are the yellow ones, and this is the outputs. And the last function tells you again some domain knowledge you can put in there. And in fact, you can build the domain knowledge at this level as well, and do that. So the important thing to remember is this domain knowledge producing higher level features. You can't, for example, feed the domain knowledge into your foundation models. It doesn't work. The foundation model works on the raw input, and the domain knowledge is what you did, and higher level you need to group them and build them. By the way, we have done this for some high-level recognition of images for in-painting, and it works exceptionally well. But I think this is a much general method could be done in other domains. So, for example, this could be a physics model of, let's say, quantum mechanics or general relativity. You can embed them into do these things. So, some of the quickly, I'm sorry, I'm running out of time. One of the biggest problems is the data we see seem to test the AI system is by validating on some examples. So we cannot quantify how well our AI systems work. For example, we don't know when they work, we don't know when they don't work. But this is also true for traditional software as well, but at least we know a large components of them we know. For example, if you use a sorting module, we know it perfectly does sorting. And similarly, if you're doing a search, it is going to work perfectly well, we know that. And we don't know about AI systems, when they will fail. Unfortunately, you need some of the models that I was talking earlier. And again, conventional software systems, we know that something went wrong, we know how to debug it. For example, at what point it has done that. But with AI systems, we know which nodes triggered, but we don't know why those nodes triggered. For example, what inputs made them to behave that way, we don't know. So debugging is a big question in AI systems. And the other one is unlearning. So for example, let's say we train the system using some false data. You want to say, oh, don't use that data anymore, that is false. But we don't know how to unlearn them except going back ab initio, that is retraining from the scratch. How to debug these foundational models, we don't know. Partial solution is like the way I said, domain knowledge integration and so on. Both BARD and JIP seem to do post-processing before emitting the output. So for example, I don't know whether you have seen, GPT sometimes answers and then clears the data quickly, something it noticed that it doesn't want to show you the data. Similarly, BARD, or sometimes they show, I'm not trying to answer this. Basically, they are unhappy to talk. For example, on BARD, or on, I think on BARD, if you ask any political questions of US, Trump or anything, it doesn't answer. They don't want to go into trouble. So you can see that these are all kind of handed at the top level, not part of the inbuilt system. So question is, how do you make AI systems robust? That is a big question open. How to minimize them? Fairness is an issue. Legal systems, if something goes wrong, how do we do these things? The AI is penetrating just about every space and improving productivity. My guess is in very few years, it's going to replace many jobs will go away: engineers, doctors, lawyers, teachers, maybe professors, and military application. Robots can build houses, roads, drive cars, fly aeroplanes, and so on. How do we manage and engage our society when this becomes a reality? Now almost no one goes to library, as most information is available on internet, for example. So the questions we have to worry about is, we used to have typists, they don't exist anymore. In most advanced countries, we don't have many bank outlets, as most do not use these outlets at all. Some banks are not even dealing with cash anymore. One of our banks decided they don't want to do anything to do with cash, everything electronic. Many nations are becoming cashless society. Everybody uses their mobile phone. Even in India, I noticed that a lot of them pay using their phones. So you can see the cash would disappear. But if that happens, potentially huge unemployment will come when all of these things become reality. So we need to teach and train our students preparing a new feature. Maybe all our students should become experts in using tools like AI systems. And AI is currently solving many problems which were thought to be impossible. and AI is becoming much more practical, and the trend will continue. We need new ways of distributing wealth. This is a big issue. It will be interesting to see. So currently AI cannot solve many problems. As I said, for example, many dynamic problems it can't solve, but the progress rate is phenomenal. I'm sure some of these domain knowledge will be included, and AI is a scary technology. Quantum computing, when it becomes a reality, this is going to cause even more revolution. Okay, to survive in this thing, I think we need to know a lot of computing, mathematics, physics, chemistry, and languages. More languages one can speak, better brain will be. So exponential growth and so on, you know, okay, I'm running out. So what I wanted to say is this curve never appeared, but this is going to happen now. The large language models and artificial general intelligence is making to push this intelligence exponentially. Thank you.
Sir,
Hello?
thanks a lot for your very informative session. It's really useful for the beginners.
I'm done.
Sir, thank you so much for your wonderful session, sir. It's really very useful for the beginners and also the people who are doing the research in the deep learning and AI. You have given a very lot and great insights of AI and as well as the deep learning. So due to the insufficient time, I opened the session for the discussions and only few questions are allowed.
Sure.
Good evening, sir. Hello. Good evening, sir. Yeah, sir, as you said, AI is evolving very fastly, but right now ChatGPT can make websites in an instant by just giving a prompt. Will ChatGPT evolve? Can ChatGPT do cyber attacks with just a prompt?
I mean that to me that these AI systems can behave like humans, you know, in some domains, and can do even better. I mean, the real fear that which I haven't really covered is that what happens if these AI systems, let's say argument's sake, they know physics well, they know chemistry well, they know medicine well, they know mathematics, engineer, all of them they know. So you don't find a single individual who knows everything. And let's assume these AI systems know everything and cross-fertilize in the sense that there may be some discovery in physics might be very important contribution to medicine or to engineering or to even AI itself. And if that becomes, then these machines becomes incredibly powerful. And similarly, they can be employed by, for cyber attack. So one of the interesting comments I heard somewhere is that, for these systems to behave perfectly well, you need huge amount of data. Remember, I made a statement that rich companies are those that have data, not money. And whoever has some data are the richest companies. So to have cyber security strong, you need high quality data. So that means the attackers will never have that much amount of data to attack you. So having large amount of data, you can build a ChatGPT kind of protector to basically stop cyber attacks, for example. This is one of the concepts people are producing in the security area, because these companies have more valuable data to protect their cyber infrastructure. They can train their models with this data, whereas the attacker would not be able to do it. However, what I would say is that, cyber security problem comes because we don't know how to code. We have errors in our systems. This is a double-edged sword. That is, if you want your computer system to be easily accessible, then you need to make interfaces a lot easier to use. And if they are easy to use, then you can break in. Like for example, these iPhones and everything, they recognize you or they look at your fingerprint. And if somebody wants to, get into your system, all they need to do is grab your phone, show your face, and then they open the system and they can access anything they want. So the very convenience is making systems vulnerable. So the question is that, ChatGPT-like systems can become incredibly strong cybersecurity models because of the kind of data they have for training. That makes sense?
Thank you, sir. Thank you for your.
Yeah. Yeah.
Any other queries?
So with no further questions, on behalf of the Kalasalingam Academy of Research and Education and ICMC 2024, we wholeheartedly thank Professor Rao Kotagiri for his wonderful talk on an overview on the integrating the domain knowledge for the enhanced AI applications. Thank you so much for spending your valuable time, sir. Thank you.
Yeah. I have sent my slides to Giri. I'm happy for you to distribute them.
Thank you so much, sir. Thank you so much. We would be happy, sir.
All right. Thank you all the best.
Thank you, sir. Thank you, sir.
Thank you, sir.
So I got that? Yeah.